Now we've already seen and used the results of differentiating trig functions, but we haven't actually looked at a formal proof. We've seen an informal proof where we just looked at the gradient of the sine curve and reasoned that it looked a lot like the cos curve, but now it's time to prove it algebraically. So if we start with proving the differentiation of sine x, then we can look at how to find the differentiation of cos x and tan x from that. Now we're going to go right back to using first principles, which means we're using this old formula where f dash x equals the limit as h approaches 0 of this. And a quick reminder of why we're doing that: we're taking some curve and we're saying if we've got some point on it x, then it has a corresponding f of x, and if we make some distance, let's call it h, that's just a little bit further along, we'll have x plus h, and this point over here will be the function of x plus h. And then we're reasoning that if we want to find the gradient of the tangent right here at x, because that will give us the gradient of the actual curve, then we can fudge it a little bit by saying, well, let's find the gradient of this secant here, and then let's make h get smaller and smaller. And that's where this formula comes from. We take the limit as h gets smaller and smaller and approaches 0 of the rise over the run. And the rise is just the function of x plus h minus the function of x, that will give us this distance here, over h, which is the run. So that's where that's come from, and you've seen that before, but a quick bit of revision. Okay, so writing this out then, we need to take f dash x as being the limit as h approaches 0 of the sine of x plus h minus the sine of x over h. Now, what are we going to do with this? Well, in a proof, we actually know the answer here. We know that what we want to get out at the bottom of it is cos x. So we're looking to change the form of this. We can't sub in 0 on the denominator here because we know we can't have 0 on a denominator. So if you're looking for a way to move forward and you're feeling stuck, you need to look at your reference sheet and think, well, how can I come up with some expression here to change these signs into causes? 2 cos A sine B is equal to the sine of A plus B minus the sine of A minus B. Now, how did I know to pick that out? Well, I've got the sine of something minus the sine of something. So looking at your reference sheet, this is the only formula that really jumps out as something that I could use. Now, I can only use this if my A plus B is equal to x plus h, and my A minus B is equal to x, which begs the question, what do A and B need to be? Now, for something like this, you might be able to spot this and solve this little problem in your head. The easiest way to do it, I think, is just to write out what you know. So we need to say, let's let x plus h equal A plus B. That can be our first equation. And then we need x, just on its own, to equal A minus B. Okay, so we want to come up with now a little expression for what is this big A and big B, because if we can come up with that, then we can change our sine of something minus sine of something else into a simpler expression like this. But we need to know what the big A is and what the big B will be. So to solve this, I think using the elimination method for solving simultaneous equations makes a lot of sense. If we add the equations, then we'll get rid of one of these pronumerals, and if we subtract the equations, we'll get rid of the other one. So let's go ahead and do both of those things. If we do equation 1 minus equation 2, then here we'll have x minus x, that gives us nothing, and we'll just have h on that side. And over here, the a minus a will give us nothing, but b minus negative b will give us 2b. So we can easily simplify that and say that big B must be h over 2. Okay, so we're going to need to use that. Now let's add the equations together. And adding them, we can see that x plus x is 2x, and we'll have our h there as well on the left-hand side. And over here, a plus a is 2a, and b plus negative b, well, the b's will disappear this time. So now to get the a by itself, we need to just halve both of these things. So big A is going to equal half of 2x, which is just x, plus h on 2. Okay, so now I've got a little expression there for big A, and for big B, I can go all the way back up here and say, look, I've got something that looks like this, and I want to turn it into that. So now I can say, therefore, the sine of x plus h minus the sine of x, so that's my whole numerator there, is equal to 2 cos big A, where big A is this, so let's put it in brackets, multiplied by the sine of b, where b is h on 2. Okay, now I can hear you thinking, how's that helped us? Well, we're really just looking for a way of changing this into something else. So let's go ahead now and substitute all of that back in up here. This is sort of like my working on the side, and that's why I've done it in red to show that it's sort of a separate section of the proof, because now I can use all of that up here. So my next line will be, we still need the limit as h approaches 0, but now on our numerator we're going to put all of this. We have 2 cos x plus h on 2 sine of h on 2 all over h. Okay, what to do next? Well, to see the way forward, I would treat this like a show that question, where we actually know what the finish line should be. We know that we want it to say cos x by the time we get to the end. And that gives me a reminder that I'm looking to get rid of this term that's got sine in it. I'm also looking to tidy up and sort of somehow get rid of this h from the numerator. And I've got this 2 over here that I also know doesn't need to be in the answer. So to me, it makes sense to take all the bits you sort of don't want and group them together to see if there's something you can do with them. So if I now just break this term up, we've got the limit as h approaches 0. And let's just break things up here. Let's just put the cos of x plus h on 2 on its own and multiply that by the rest. So we're going to have 2 sine h on 2 over h. Now, can I tidy this up even more? Can I get this to look different? Well, multiplying by 2 is the same as dividing by a half. So if I actually took that times by 2 and instead divided by a half, then down here I'd have a half. Does that sort of make sense? And I could actually write that much more tidily by writing it as h over 2. Now, why am I doing that? Well, I'm just trying to get various parts of my equation here to talk to each other so that they look like something I can recognise. Now, sine of h over 2 over h on 2. That wouldn't jump out at me for any special reason unless I'm thinking about h being really, really small. And sure enough, we're going to make h be really, really small. Now, we've already learnt that as, let's think about what we know here, as x approaches 0, we know that the sine of x gets very, very close to being equal to x itself. That's something that we learnt at the start of this topic. So in other words, if you take one of these things and divide it by the other, if they're roughly the same, you'll get 1. So here, if we've got the sine of h on 2, and we're dividing it by h on 2, and h is going to be very, very small, we can see that both of these terms are going to be roughly the same. So at this point, I can say this is equal to the limit as h approaches 0 of the cos of x plus h on 2, I'll just leave that part, multiplied by 1. Now this is a proof, so I'm trying not to do too many things in one go. I've effectively just taken this whole part here and converted it to 1. All right, now I'm ready to take the limit as h approaches 0, which means I can virtually just sub 0 in here. Okay, what will we have? X plus 0 on 2, we'll just have x, won't we? So sooner than you might have thought, we've come out at that nice simple answer, which is the one that we were sort of expecting. So this is a simple proof really for how we differentiate y equals sine x by first principles, and what we get is the first derivative being cos x. Now let's have a look at how we can differentiate cos x. Now we could use the same process here, but we could also use a shortcut. And that shortcut is that we can always rewrite trig functions that involve sine or cos as the other one if we remember that simple fact that inside a right angle triangle, these two angles always add up to 90 degrees. So if we call this one, say, x, then this one would be 90 degrees minus x, right? Because these two will add up to 90. Or we could call it pi on 2 minus x if we're working in radians. And we know that the sine of this angle would be opposite over hypotenuse, but that would be the exact same two sides as the cos of this angle, which would be adjacent over hypotenuse. So anytime we want to adjust cos and turn it into sine, we can do that as long as we just change the angle from x to 90 degrees minus x. And now we're ready to just use the result that we already had because we've just proven how to differentiate y equals sine x. Now, this isn't y equals sine x though, it's y equals sine of something a little bit complicated. So let's use the formal version of the chain rule and say that if we let u equal the part that's a bit complicated, the 90 degrees or pi on 2 minus x, then we can now say that y is equal to the sine of u, and we can find dy du very easily because we've just proven that result. It's just going to be the cos of u. And we can differentiate u with respect to x also very easily. We just get -1 because we ignore this term, it's just a constant, and differentiating negative x with respect to x, we just get -1. So that means that dy dx is equal to dy du times du dx, because obviously the du's cancel. We've seen this before with the chain rule. And so what that gives us is the cos of u multiplied by -1. So we have the negative out the front, and then we have cos, but we don't want to put u into our answer because what we're differentiating doesn't have any u's in it. So instead of writing down the u, we write down what u is, and we get this part in brackets. And now to finish it off, we made this substitution in the beginning so that we could have a workaround for differentiating the cos of something. But here, we've ended up with the cos of pi on 2 minus x, and that's exactly the same as the sine of x. So we can make the substitution here. We can put a little explanation here if we want to, but cos of pi on 2 minus x is equal to the sine of x. So that just gives us the nice simple result of minus sine x. And the formal proof for differentiating y equals tan x was already shown to you in the video with the informal proofs, because this is just a nice simple use of the quotient rule. Let's do it again though quickly, just for some revision. If we rewrite this as sine x over cos x, now we can use our quotient rule, and if you like to write your ingredients on the side to make sure you don't mess it up, that's totally fine. If u is sine x, then u dash will be cos x, and if v is cos x, then v dash will be negative sine x. So now dy dx will be v times u dash, so that's cos x times cos x, that'll be cos x all squared, which we can write like that, minus u v dash. Now that'll be negative sine squared x, won't it? So if we're subtracting negative sine squared x, we're actually adding sine squared x all over v squared. Okay, can we tidy this up at all? Yep, sine squared x plus cos squared x equals 1. And that gives us this result. And we can tidy that even further by saying that is sec squared x, which is the result we've been using.